Why study Laplace transforms? Well, Laplace transforms are a technique for solving higher order differential equations. Now, that begs the question, why study them if we already have some excellent methods for solving higher order differential equations? Right now, we're able to set up characteristic equations. Those tell us the complementary solution. We're able to use method of undetermined coefficients to find solutions to the inhomogeneous equations we come across. And we can even use variation of parameters, say, if we want to solve an inhomogeneous equation with some kind of strange right-hand side that doesn't conform to one of our usual patterns. So with all these powerful techniques at our disposal, why study another one? Long story short, there are a few forcing functions that we can deal with, like right-hand sides I'm talking about, that arise in physical problems that are discontinuous. And none of the techniques that we've studied work for discontinuous functions, or at least they are extremely difficult to get to work. So recall that a discontinuous function is a function that has a kind of jump in it. And Laplace transforms are a way of dealing with those kinds of functions. So let's begin this discussion by just defining what the Laplace transform is. If you have a function f, lowercase f that is, defined for positive real numbers, then we can define the Laplace transform of f, which we often denote by a capital F or the script L attached to f. And this new function, capital F, or also called the Laplace transform of f, is defined in this way. Now, what's interesting about this function is that it is a function of a different variable, s. So the original function, lowercase f, could be thought of as depending on t, whereas the new function, capital F, depends on s. And it turns out that capital F is not necessarily going to be defined for all s, but it, in practice, is defined for most s, for most functions f. We're not going to really worry ourselves too much about the domain. We can, you'll see that these domain issues aren't really an issue. Anyhow, this is the definition of the Laplace transform of lowercase f. Right, so let's compute the Laplace transform of our first function, f of t equals 1. If we want to compute a Laplace transform, we can proceed from the definition. The definition of the Laplace transform is this. I've written it here. And if we use the fact that our function is simply 1, that we want to take the Laplace transform of, substitute 1 in here, and the Laplace transform becomes simply this integral, which, and I leave you to check this on your own, if you do a u substitution, you get this, and evaluating from 0 to infinity, you end up with positive 1 over s. So, we conclude that the Laplace transform of 1 is 1 over s. That's our first Laplace transform formula, so congratulations. Let's take the Laplace transform of something a little bit more interesting now. Let's try e to the kt, where k is some constant. So if we want to take the Laplace transform of e to the kt, we simply apply the definition. We put e to the kt inside the integral that defines the Laplace transform, and we need to compute this integral. We can just use the product rule. Note that t is the variable of integration. So when we do a u substitution, u equals k minus s times t, then du is k minus s dt, and so that's where this 1 over k minus s comes from. And we're evaluating from these endpoints. where of course it's understood that we're taking the limit as t approaches infinity. And if s is greater than k, then this is e to a negative power, which is approaching 0 as t approaches infinity. So we're left with 1 over s minus k. The k minus s switched to s minus k because we're subtracting. I just wanted to write it in the cleanest possible way. And there you are, your second Laplace transform formula. And if you're wondering why the heck we're doing all of this, I suggest you wait till the end of this show, and we will get an application of all this. Suppose you have a function f, and it's differentiable, meaning it has a derivative. And suppose you already know the Laplace transform of that function. My question for you is there an easy way to compute the Laplace transform of the derivative of your function? And of course I wouldn't have asked this question unless the answer were affirmative. If you want to take the Laplace transform of the derivative, well, simply use the definition of the Laplace transform, and then do a little integration by parts here. And if you do that, with u being e to the minus st and dv being f prime of t dt, then you get this for du, this for v, and integration by parts yields this. And then assuming this limit approaches 0 as t approaches infinity, which it usually does, you end up with simply negative f of 0 plus s times. Now this is an important point here. I took the s out of this integral. Now that's perfectly allowed because this is an integration with respect to t, not s. So s is a constant as far as this integral is concerned. So it's okay to take the s out of the integral. Once I take the s out of the integral, what we're left with is precisely the integral from 0 to infinity, f of t e to the minus st dt, which is precisely the Laplace transform of f. So what we've just found is that so this gives us minus f of 0. This integral amounts to s times the Laplace transform of f, which I've written here. And there's your formula for the Laplace transform of a derivative. It is equal to s times the Laplace transform of the original function minus the original function evaluated at 0. So now that we have a first derivative formula, why stop there? Let's get a second derivative formula. Recall that the Laplace transform of the derivative of a function is this, where you'll have to excuse me, I forgot a minus sign here, but I believe I fixed it in the work that follows. So it's minus g of 0 plus the s times the Laplace transform of g. So let g be the derivative of f, and then we can rewrite this formula as the Laplace transform of g prime. This is a subtle point, so make sure you understand what I did here. We had this formula from the previous slide. Then I said, suppose g were equal to the derivative of f, then g prime would be the second derivative of f. So, substituting f prime for g, we end up with a formula for the second derivative of f. Kind of clever, if you can follow. So substituting g equals f prime throughout this expression gives us this expression, this equation. And then we can use the Laplace transform formula for the derivative of f again. And it is that. And then when we expand and simplify, we end up with this when the dust settles. We have s squared times the Laplace transform of f minus sf of 0 minus f prime of 0. And that is your formula for the second derivative Laplace transform. Oh, spoiler alert, I guess. If we have a Laplace transform of a linear combination of f and g. So suppose you have a times f of t plus b times g of t. It turns out that you can just, it turns out the Laplace transform operator is a linear operator, meaning you can take the a out, take the b out, and you can also separate them with a plus sign. You're going to have to excuse these annoying typos. I don't know why there were two plus signs there. A Laplace f plus b Laplace g. And this is another way of saying that is a capital F plus b capital G. So how do you prove it? Well, just apply the definition as we always do. If you do that, we're integrating e to the minus st against this linear combination, and then just expand and take the a's and b's out of the integral, out of the integrals, which is perfectly allowed since the integrals are linear. And then these integrals that we're left with are precisely the Laplace transforms of f and g. You're going to have to excuse these spoilers. This is what we're about to prove. Let's prove it. So suppose we want to find the Laplace transform of sine omega t or cosine omega t. Well, let's do it. The Laplace transform of sine omega t is this, which after plugging into a computer, if you didn't want to plug into a computer, you could do this as an integration by parts twice, then solving for your integral. It's a long process, but you end up with this in the end. And when you take the limits, the limit as t approaches infinity and 0, and you plug them in here. When the dust settles, you end up with omega over s squared plus omega squared, as we have here. And for the Laplace transform of cosine, I just went and plugged that into a computer again, and took the limits 0 and infinity. And so just to be clear, as t approaches infinity, this exponential term is approaching 0 much faster than this is approaching 0, and this is approaching 0. And as a result of that, the only thing that matters is these values when t is equal to 0. When you plug those in, well, you have cosine 0 is 1 and sine 0 is 0. So that's where these came from, if you're curious, as well as this. Now, this is going to be the last rule in this presentation, the power rule. Let's compute the Laplace transform of t to the n for a positive integer n. Well, if you want to compute the Laplace transform, we use the definition. Put your function inside the integral next to e to the minus st dt and evaluate. So if you do an integration by parts, let u equal t to the n, dv is this, all this, you end up with this. This is just uv minus the integral of v du, the standard integration by parts formula. But then when we do all this, it turns out this whole thing is just 0, because e to the minus st is approaching 0 so fast that it doesn't even matter that we have a t to the n here. So you get 0 when you plug in infinity, and you also get 0 when you plug in 0. So this whole thing disappears, and you're left with this. N over s times the Laplace transform of t to the n minus 1. This should be an integration with respect to t, of course. Alright, and so we have this, but we haven't really solved the problem yet. We've just expressed the Laplace transform of this function in terms of the Laplace transform of another function. But the idea is that you could keep going. You could then do the same thing to this and get a formula for this in terms of n minus 2, then n minus 3, then n minus 4. But eventually you're going to reach t to the 0, which is just 1. And we know that the Laplace transform of 1 is 1 over s. So in the end, when you've done this process n times, you're going to end up with n factorial, n times n minus 1 times n minus 2 times all the way down to 1. And you'll also end up with n plus 1 copies of s in the denominator. So this is our formula. I think I'll make it a homework problem to prove this formula by induction. So you can have fun with that. So we computed all these Laplace transforms. Now it's time for you to find out why. Here is one application of the Laplace transform. We're going to use it to solve a differential equation, actually an initial value problem. So here's a differential equation. Y is a function of t. Of course, you already know how to solve this. It's an inhomogeneous equation. So you would solve it the usual way, but we're actually going to use this new method of solving it. Let me show you. So we're going to use Laplace transforms. The idea is to take the Laplace transform of both sides of the differential equation. Now already, that might be a bit confusing. Well, the idea is that the left-hand side is a function of time, ultimately, and the right-hand side is also a function of time. We don't happen to know what y is yet, but we know that the left-hand side is equal to the right-hand side. Therefore, the Laplace transform of the left-hand side should equal the Laplace transform of the right-hand side, if you follow. So let capital Y be the Laplace transform of our unknown function. And what do we have? Well, we take the Laplace transform of both sides of this differential equation. Then we use linearity of the Laplace transform. And we also use the Laplace transform formula for e to the kt, with k equals negative 1 in this case, which you'll recall was 1 over s minus k. And on the left-hand side, we use our derivative formula, our second derivative formula. So the Laplace transform of the second derivative of a function is s squared times its Laplace transform minus s times the value of the function at 0 minus the value of the function's derivative at 0. Then 3 times the Laplace transform of y is just 3 times capital Y of s. And on the right-hand side, we still have 1 over s plus 1. So, what do we make of this? Well, first of all, y of 0 is 1. Y prime of 0 is 2. What else do we know? Well, we can solve for capital Y. This is an algebraic equation of capital Y. If you don't believe me, just ask yourself, do you see any derivatives of capital Y anywhere here? No, you do not. We can easily solve for capital Y by collecting like terms or just using a computer. So if we take this equation that we have here and solve for y, you end up with this, which I've written here. Now let's apply partial fractions to the right-hand side. Now I know what you're thinking right now. Why in God's name did you use Laplace transforms for this problem? If we have to now do partial fractions to this awful thing, when we had a perfectly good method of solving this problem without partial fractions. Well, you'll see. But for now, let's go about solving this problem. So we're going to break this apart using partial fractions. You can simply use the apart formula in Mathematica to do that. Simply specify the fraction you want to break apart with partial fractions and the variable with respect to which you're doing partial fractions. This is useful because sometimes you'll have some extra constants in here that you want to treat as constants rather than a variable, so it's important to specify the variable when you're doing partial fractions. So you end up with this. That's a plus sign. It's kind of hard to read. These are all plus signs, actually. And I took the liberty of splitting this apart into 9/4 over s squared plus 3 plus 3/4 s over s squared plus 3. So that's what I've written here. And now we recall a couple of things. Recall that the Laplace transform of the sine of omega t is this, and the Laplace transform of cosine omega t is this. Well, we basically have those here and here. Also recall that the Laplace transform of e to the kt is 1 over s minus k, which looks an awful lot like what we have here. Now, I've rewritten these things suggestively for you. So I've taken the 1/4 outside and written this as 1 over s minus k plus a giant constant times omega over s squared plus omega squared, where omega is the square root of 3, plus 3/4 times s over s squared plus omega squared, where omega is the square root of 3. Maybe I'll write that down. Omega equals the square root of 3. I'm getting pretty good at using this mouse pad, aren't I? I mean, that's not bad. Alright, anyway. So, we know that the Laplace transform of y is this. So, we conclude, using these formulas, that the original function y is this. Just check that you can check that the Laplace transform of this term here is this, the Laplace transform of this is this, and the Laplace transform of this is this, using these three formulas. And so why did I put an asterisk here? Well, because I've just done something very devious. We've shown through rigorous computations that the Laplace transform of our unknown function y, which we denoted by capital Y, is equal to all this. We also went about finding a function whose Laplace transform is this. Now, I just made, as I said, a devious assumption that if the Laplace transform of this function is this, then this is the correct function. Depending on who you are, that might make no sense. It might be completely obvious to you. If it's completely obvious to you, that just means you don't understand it, because the proof of that is pretty difficult. But it turns out, yes, that if you know the Laplace transform of your function, then and you find a function whose Laplace transform is that, then that is the only function whose Laplace transform is that. And so this must be the solution. I'll let you chew on that.